Welcome back to Physics 371 online. What I'd like to do now is give an introduction to electromagnetic induction, the phenomenon, and the way that we describe it using something called Faraday's Law. What we saw last time was that a conducting loop moving through a magnetic field leads to an electromotive force and, if the loop is a closed loop, a resulting current flow due to the force of the magnetic field on moving charges in the loop. All right? And the question arises, what if we hold the loop stationary but cause the magnet to move? The same relative motion would take place, but what would be the result if we measured to see if there's any current flowing in the loop? And experimentally, you're probably not surprised to find out that the exact same current will also flow through the loop in this second scenario. But let's think about these two things, how they're the same and how they differ. First of all, the moving loop that we considered before results in a force on moving charges, the charges that are in the loop as it's moving, due to the magnetic field. And if that force causes charges to move in a net way around the loop, we get a current as a result. That makes sense. That's just the Lorentz force law. But in the case of a moving magnet, where the loop of conducting wire is held stationary, we still must have some kind of force, but it's a force on stationary charges. And the question comes up, what is it due to? It can't be due to the magnetic field itself, because we know that magnetic fields only exert forces on moving charges. Now you might say, well, isn't it the same thing? Isn't a moving magnetic field and a stationary charge the same thing as a stationary magnetic field and a moving charge? And in one sense, yes, it results in the same phenomenon. But what must be acting on the stationary charges if it can't formally be the magnetic field? And it only takes a little bit of thought to realize that besides gravity, which for electrons and charges like that is very, very weak, the only thing that we know of that can produce a force on a stationary charge is an electric field. And so if this moving magnetic field results in a force on charges, it must be due to an electric field. And so let me just go back to one of the previous slides to remind you what this looks like. Here was the case of a loop of conducting wire moving to the right through a region where there is a magnetic field. And what we're saying is, if instead the loop is held fixed and the region where the magnet is located, or the magnet itself is moved to the left, we get the same thing happening. But we're going to say now that what's going on, if the magnetic field is moving, is that the charges are experiencing a changing magnetic field. And as a result, an electric field arises from that change. So let's see how that works out in detail. We can relate it to the changing magnetic field in the following way. First of all, we already know that from our treatment of this motional EMF, that the EMF that's produced is the loop integral of E dot dl around the closed loop, and that we showed that that's equal to minus d phi dt, so the negative of the time rate of the change in flux through the loop. And now it's important to point out that this is not an electrostatic field. If it were an electrostatic field, we know that the integral of E dot dl around a closed loop would simply bring us back to the same point we started at, and the potential would be exactly the same. So this integral would give us 0 if E were an electrostatic field. So this field is very different. It's a field that in some sense loops around in a way that this integral gives a non-zero result. So we sometimes call this kind of a field a Faraday field. It is an electric field. It has similar properties to an electrostatic field, such that it causes forces on moving charges, or it causes forces on stationary charges, but it's produced in a totally different way. So we can also express this equation, which is something that we call the integral form of Faraday's law. We can express it in a differential form, which is a little bit more compact. And we can do this just through using Stokes Law. Remember that Stokes Law tells us that the integral of the curl of a vector function dotted into dA over a surface is equal to the integral of that vector function dotted into the path element all the way around the closed loop that bounds the surface. And so we can realize that Stokes' law then tells us that the left-hand side, if we replace it with minus d phi dt, and then simply use the definition of magnetic flux, phi is equal to the integral of b dot dA over some surface, so we pull the time derivative outside the integral, we see that we can write this as the integral over a surface of the time rate of change of the magnetic field dot dA. And here I've put in a partial derivative sign because we expect that B should not only depend on time, but also depend on space, on x, y, and z in some region. And so it's appropriate for us to write this as a partial derivative in the most general case. So now compare the left-hand side, which is the integral of the curl of E over this surface, and then the right-hand side, which is the integral of dB dt dot dA over the surface. And if those two integrals are always the same, the only way that can happen is if the curl of E is equal to minus dB dt. So by inspection, we can realize that those two quantities are equal to each other, and now we see a little bit more clearly where these Faraday fields come from. We see that they're fields that have a non-zero curl, and that the curl, which tells us that these fields circulate around in space, the curl is equal to minus the time rate of change of the magnetic field. So now we know that there's two ways to create electric fields. We can use charges. From Gauss's law, we remember that del dot E is rho over epsilon 0. So those kinds of fields have divergences that are related to the charge density. Here, we can also create electric fields by having changing magnetic fields that change in time. And the more rapidly they change in time, the stronger these electric fields will be. So this is referred to as a Faraday's law in differential form. And just note that for a time-independent magnetic field, such as what we assumed leading up to this chapter, we talked about magnetostatics. So if the magnetic field is time-independent, then this equation, this version of Faraday's law, reduces to the familiar equation that we know holds for electrostatic fields. So what we've basically done now is we've taken this original expression for the curl of E and generalized it to treat the special case where there are changing magnetic fields, and in that case the right-hand side will not be zero. So there's a simple rule to keep track of the direction of the induced current if we ever have changing magnetic fields or changing magnetic fluxes through a conducting loop. The question arises, which way will the induced current flow? And the minus sign in Faraday's law gives us one way of accounting for that, but it's kind of complicated to chase that down all the way through the expressions like Faraday's law. So there's a simple rule that just tells us what that minus sign means in Faraday's law, and it's a simple way of remembering how the induced current will flow. It's called Lenz's law. Lenz's law says the induced current resulting from electromagnetic induction flows in a direction such that the magnetic field it produces, the magnetic field produced by the induced current, tends to oppose the change in magnetic flux that induced the EMF in the first place. So that Lenz's law tells us that a Faraday electric field is a phenomenon that always opposes whatever it was that gave rise to it in the first place. So let's work out two examples using just a circular conducting loop in a region where there is a magnetic field perpendicular to the page. So here's the first one. Here's a circular conducting loop, and the circles with dots are trying to tell us that there's a magnetic field pointing out at us. And let's consider the case where that magnetic field is out of the page and it's increasing in magnitude, so that the field lines are coming out toward us and they're getting stronger. Maybe we have this loop in between the poles of an electromagnet and we can crank up the current so the magnetic field is getting stronger. So since it's coming out of the page and it's getting stronger, the induced B, the B produced by the induced current that must flow around this loop, should oppose the changing magnetic field. So that means, according to Lenz's law, that the induced magnetic field should point into the page, because that opposes the increasing magnetic field. And now, using the right-hand rule, in order for there to be an induced magnetic field into the page, that must arise from an induced current that flows clockwise around this loop. So the induced current in the loop is clockwise. Take a few minutes to digest that and make sure that you understand the reasoning. Let's do a similar example now, but we have this closed current loop, or this closed conducting loop. There's no current originally flowing in it, but now there's a magnetic field into the page, which is what the X's indicate, and let's assume that that magnetic field is decreasing. Maybe we have the loop between the poles of a magnet and we're turning down the magnet current. So the magnetic field strength, even though it's pointing into the page, the magnetic field is getting weaker. Now this one can be a little bit confusing, but think about it this way. If the field is pointing into the page and it's getting weaker, what we want to have to oppose that is an induced B that also points into the page to reinforce the weakening magnetic field. So Lenz's law says, just to summarize, the induced B should be into the page to oppose the decrease, and the only way you can have an induced B into the page is if there's an induced current in a clockwise direction around the conducting loop. So we end up with the same answer, but it arises from two completely different situations. Now, last thing then is, what if we want to calculate the induced electric field that is mentioned in Faraday's law? An electric field that arises from a changing magnetic field or a changing magnetic flux. How do we calculate it? And it's really kind of clever. We can exploit a really neat symmetry between magnetostatic fields and Faraday-type electric fields. And it's a mathematical symmetry that we find if we consider the relationship between Faraday's law and between the Amperes law. So Faraday's law says that the curl of E is minus dB dt. Amperes law says that the curl of B is mu naught J. So what we have on the right-hand side of these curl equations is some kind of vector function. In the case of the Faraday's law, it's a time rate of change of a vector function, but it's a vector function nonetheless. On the right-hand side of Amperes law, we just have mu naught times J, the current density. So now let's assume that we have a pure Faraday field. So we're in a region of space where there's no electrostatic fields because the charge density is 0. In that case, now let's consider excuse me, let's consider the divergences of these two fields. So del dot E, which is rho over epsilon 0 in general, according to Gauss's law, will equal 0 in a region of space where there is no charge density. Del dot E is equal to 0, and we know that del dot B is equal to 0 everywhere. So now compare the two equations on the left with the two equations on the right. The two equations on the left, del cross E is equal to a vector function. Del dot E is equal to 0. On the right-hand side, del cross B is a vector function. Del dot B is equal to 0. So what we see is that E and B satisfy very similar kinds of equations. And assuming that they obey the same boundary conditions, where the electric and the magnetic fields would go to 0 as distance goes to infinity, what we can say is that the Faraday electric field, E, is produced by dB dt, negative dB dt, in exactly the same way that the magnetostatic field, B, is produced by mu naught J. So what we can do is translate the Biot-Savart law that tells us how to solve for B into an expression for E. And even more usefully, we can come up with a modified version of Amperes law as well, which is really just Faraday's law. So let's see how this works out. Biot-Savart law, remember this, in the most general case for a volume current density J, it produces a magnetic field using this equation, which we very rarely use because it's awfully complicated. But if we now make the substitution that we replace mu naught J with minus dB dt, we can plug that into this equation and come up with an expression for E. And there's no name that I know of for this equation that results, but replacing B with E and replacing mu naught J with minus, there's a minus sign here, and a dB dt, we have an expression for this kind of Faraday field that's produced by a changing magnetic field, in much the same way that a magnetic field is produced by a current flow. Okay? And more usefully, when symmetry permits, is to use all the tricks associated with Amperes Law that we use to solve for B, and use these tricks to solve for E starting from Faraday's law. So Amperes Law, remember, in a empty region of space where we just have current flowing and there's no material, is integral B dot dl around a closed loop is mu naught times I enclosed, the current enclosed by the loop. And the electric field version of this is simply Faraday's law. We've seen this already in the integral form. Integral E dot dl around a closed loop is minus d phi dt. So we can use all the symmetry arguments and the right-hand rules that tell us if there's a particular direction of current flow, what symmetry of B would that imply? We can use that same kind of reasoning for the cases where we have a changing magnetic flux. And if we know something about the direction of the field, the magnetic field that produces that changing flux, then that tells us, through the right-hand rule, how E is oriented in space. And that allows us to choose a loop around which to integrate the left-hand side, and then ultimately, if the symmetry is high enough, to solve for E. So there's some examples in the text. Please take a look at those and realize that this is going to take some practice, and I will work out an example in class. And that's where I'll see you.